this on? Okay, so good morning, ladies and gentlemen. Welcome back after the spring break. Well, you already had the first class on April 1st. I hope you enjoyed Rich Muller's lecture on climate. You did, right? Good. So we'll talk, we swap the topics a little bit. Before I start on this, let me again remind you that the next time we meet, this Tuesday, you'll be sitting sort of one seat apart, getting ready for the exam. We have a midterm on Tuesday. The format is exactly the same as midterm 1, which is there will be 2 parts, a multiple choice for about 20 questions and a short answer part where you'll be given 3 questions and you'll have to write roughly a paragraph for each. Again, you are allowed a single piece of paper, letter-sized, where you can write notes in any type, shape, or form you wish on both sides. I would encourage you to, well, it will clearly be a new set of notes. I would encourage you to keep your last set of notes from the midterm 1, hopefully. Write this one for chapters 5 through 8, which is what we'll cover on the second midterm. And then for the final, you'll be allowed 3 pages or pieces of paper. And so you can keep one from each midterm and then write one more. Generally speaking, don't try to write too much information in it so that you spend all of your exam time looking for that one number that you really needed to find. Typically, we hope most of the, or we try to make most of the questions be conceptual rather than specific, but there, of course, will be variations. And again, you can put any information as long as you don't need optical devices like microscopes to decode it. Do you guys have any questions about exam? So again, I think I said that we will include chapter 9 on this midterm, and then given some reshuffling in topics and the fact that you will not have had time in discussion sections to talk about radio waves, infrared, and UV, that is the chapter 9, we'll leave this topic off. It will be on the final, as well as the chapter 10 on global warming. And so the midterm will cover 5 through 8, so 4 chapters, 5, 6, 7, 8. And then everything else will be on the final. The final will be inclusive. We'll probably have a little bit more coverage on the last part of the course, but also will include information from the entire sequence. Yeah. There will be no questions for 1 through 4. Well, there will be no specific questions for 1 to 4. Of course, I hope that you still remember basic concepts. You know, physics isn't compartmentalized often, so things like the fact that energy is conserved sometimes comes up. But there will be no specific information from chapters 1 through 4. Hopefully, you'll still remember it before the final and for the rest of your life. Any other questions? Now, of course, there's some overlap between 4 and 5, radiation and nuclear power, but again, overlaps in topics sometimes allowed. Specifically, we'll focus on material between 5 and 8. Okay, so let me start my iClicker. Oops. So the topics for today is invisible light, not the picture of Evgeny Nabokov, although it's partially related. Oops. No, that's not it. This is it. So before the break, we talked about electromagnetic waves. We talked about the fact that we see by detecting electromagnetic radiation in our retina, our optical sensors that are sitting in the back of our eyeballs called retinas that detects energy carried by very short wave electromagnetic radiation, carried by oscillations that look like this in space. Electromagnetic waves is a sequence, wave-like sequence of oscillating electric and magnetic fields, like this, propagating in space in some direction in such a way that oscillating electric field produces an oscillating magnetic field. Oscillating magnetic field in turns produces an oscillating electric field, and they feed on each other, producing this continuously waving, oscillating structure pattern that propagates in space. And we describe it by two distinct or important quantities, actually three quantities. One is the frequency with which this oscillation happens in time. In other words, how many beats per second or per nanosecond, how many beats per unit of time, how often the electric and magnetic field flip sign in unit of time. So how often this happens per nanosecond is described by frequency. And then how far apart in space the ridges of the electric fields, the highest peaks of electric field are spaced, is known as the wavelengths. The ratio between them tells us about how quickly this pattern propagates in space, and this is the speed of light, the ultimate speed limit for everything in the universe, as far as we know, the highest possible speed that can ever be achieved. So the speed of light is the speed with which this pattern propagates in space in this direction. And so the speed of light is constant. The speed of light is 300,000 kilometers a second, or 186,000 miles a second, is a very large number. That is determined by laws of nature, as described to us by James Maxwell and Albert Einstein. But of course, the frequency and the wavelengths of radiation is something that we can control. The frequency and the wavelengths of radiation is typically determined by what produces this pattern of oscillating electric and magnetic fields. And this pattern can be produced by multiple sources. The easiest way to produce a electromagnetic wave is in fact a device like this. It's otherwise known as an antenna. Well, actually, this antenna is not producing anything. It doesn't have any electricity flown to it, but this is an antenna that can detect electromagnetic radiation. This is an antenna that can produce electromagnetic radiation. It's basically a piece of wire. It's a stick. It's a metal stick. I can connect a source of electricity to this piece of wire, to this stick here. And then this source of electricity will actually produce oscillating electrical currents, oscillating, changing electrical currents that will flow along this antenna back and forth. So I have a source here that will produce an oscillating AC electric current, similar to oscillating AC electric current that's produced by, say, a spinning turbine. There's an electrical circuit that will produce send current flowing towards the end of the antenna, then at some point the reverse direction flow back. So if you have a piece of wire, you start sending currents through it and make it oscillate back and forth. This arrangement will always produce an oscillating, changing in time electric field. So electrons that travel back and forth, each of the electrons produces an electric field. Combined together, they produce a sizable electric field. Current flowing back and forth also produces a magnetic field. Together, they'll produce an electromagnetic radiation. And this is exactly how antennas work. Antennas produce a pattern of electromagnetic fields by sending electrical currents back and forth throughout an antenna that's shaped appropriately. The simplest antenna is a straight line. Currents flow back and forth this way, and that produces an electromagnetic wave that travels primarily perpendicular to the antenna. As it turns out, first of all, let me demonstrate to you that this actually does happen. So here are the two pieces of antenna. This is known as a dipole antenna for some technical reasons. Dipole is something that has two poles, like magnetic compass. This thing sort of has two poles. Is whenever electrons are, whenever the current is positive on this side, it's negative on this side. So this dipole antenna has kind of two ends. One is typically positive and one is negative. And the direction of positive and negative continuously flips. Positive, negative, positive, negative. So, well, I'll do this with this antenna. It's a slightly more high power source. Here I'll hide this antenna for now. I have a source of electromagnetic current. It produces oscillations at a frequency of about 3 megahertz or so. I forgot exactly the number. Yeah, I think it's about 3 megahertz or so. So 3 million times a second, electric current flows through these ears. Now this thing is a receiver antenna. It's exactly the same, two sticks, two pieces of wire, but the only difference is that there's no power source. I have no batteries here. The only difference is that I have connected, or James here for our lecture demonstrations, has connected a little light bulb between the two pieces of antenna. So nominally, if I'm not connecting this antenna to any power source, there's no current flowing through the light bulb, and the light bulb is dim. I can make electrons run in this wire by either connecting this power source to an outlet or by making electrons move in this wire when they sense an electromagnetic field, electromagnetic wave. And here, very close to this antenna that's now transmitting electromagnetic wave, the receiving antenna can pick up the energy and produce visible light. So the electromagnetic wave is an example of sending energy that can be sizable, enough to light this 10-watt light bulb over significant distance. You will notice that the intensity, the brightness of this light bulb will decrease as I go further away from the antenna. That's normal. That's, you know that very well if you're driving a car and you're listening to a, say, FM radio or AM radio. The farther you go from the source, say, you're listening to some San Francisco station. If you're somewhere in the South Bay, your reception will be worse than if you're in, closer towards the station. I'm listening to the Sharks games often on the radio when the Sharks play in San Jose. The transmitter in San Jose, somewhere in the North Bay, the reception is not so good. So the further you go from the transmitter, the weaker the signal becomes. The energy sent out by the antenna gets spread out over a larger distance, and so the energy received by another antenna becomes smaller and smaller as you go further out. The other interesting thing to notice is that while the intensity of the electromagnetic radiation is very high, if I place the two antennas parallel to each other, it becomes smaller if I make them perpendicular to each other. So these dipole antennas are directional. Right? Very little signal this way, a large signal that way. The reason for this is that this antenna produces electric fields that tend to go in this direction. The current tends to move along this wire, and so it's much more natural for this electric field produced by this antenna to move electrons in the reception wire this way. So if I orient the antenna this way, the electrons like to oscillate in this direction along the primary antenna, but not in the direction along the receiver antenna. So the intensity that the antenna picks up when it's not aligned with the transmitter is low. The other thing that you may notice is that if I go out here, the reception is also very low as well. So, I'm separated from that antenna only by a yard. I can separate these antennas by a yard. Intensity is high here. But if I go same distance along the direction of antenna, no radiation is visible. So these dipole antennas are very directional. They emit almost no radiation along the direction of the antenna. and they emit primarily large intensity in the direction perpendicular to it, in there. Which brings up an interesting point. So here's on the page a picture of a typical transmission tower, transmission antenna. It has a whole bunch of sticks sticking out of it. Each of them corresponds to transmission of a radiation with specific wavelengths. Typical antennas like this, these dipole antennas, are most efficient for reception of radio waves whose wavelengths is a multiple of the length of the antenna. This particular antenna is most efficient for a wavelength that's exactly twice the size of this antenna. And so it can receive radiation that has the wavelengths of a couple of meters. This is sort of a yard and a half, 3 meters or so. Same for transmission. Transmission is most efficient when the size of the antenna is either half or a quarter of the wavelengths the antenna is trying to transmit, which is why radio waves or antennas that receive or transmit rather FM radio, FM, corresponds to, so here's radio waves. FM corresponds to frequencies of about a megahertz or so, or hundreds of megahertz. 98.5 kFox, that's the Sharks radio station, corresponds to the frequency of 98 megahertz. So that's the wavelengths of roughly 3 meters or so, right? If I'm computing it right. An antenna of about a meter in the size will be effective transmitting that kind of radio waves. Long waves, say KCBS is the AM station at 740 AM, corresponds to 740 kilohertz frequency, or roughly a megahertz, wavelengths of 300 meters. And so antenna that transmits that most efficiently has the size of 300 meters divided by 4, 75 meters. And so that's why antennas for AM radio for TV stations tend to be long, tend to be tall, like this. And the antennas that transmit FM transmissions tend to be shorter. Antennas in your cell phones can be short because they are designed to receive typically high frequencies of gigahertz corresponding to low, small wavelengths. Transmitters, antennas that transmit like this one in my iClicker, or antennas that transmit Wi-Fi signals for the wireless routers tend to be short. They transmit at high frequencies, and therefore that can be a little bit shorter than AM radios. Do you guys know why antennas are vertical? Why TV towers are tall buildings sticking up, and why the TV towers are towers standing upright instead of long buildings along the road somewhere? TV transmits at a relatively low frequencies. So again, wavelengths of shorter than AM radio but longer than FM radio, wavelengths of typically of hundreds of meters or so. And so again, since the most efficient transmission is done with the antenna that's a quarter of the wavelengths in size compared to the wavelengths of the TV, the antennas tend to be tall, tend to be long, rather. And now the reason that they stand upright is because of this effect, that antennas don't transmit along their direction. They transmit very efficiently in the direction perpendicular to the antenna, but not very well along the direction of the antenna. So if you're building a TV tower, a TV station, and you want to serve customers all around you, you don't just want to serve customers in San Francisco, but say not in Marine, you're building an antenna that's standing upright. In that case, the antenna transmits very well in the direction perpendicular to it. And so everybody around the TV station, San Francisco, San Jose, Oakland, and even somewhere in the Pacific will see the TV signal relatively well, and the birds flying above the antenna don't get fried. So in other words, the power transmitted up into the sky from a vertical antenna is small. The power transmitted by the antenna in the perpendicular direction, in the normal direction, is maximal. So that's the reason why most of the long wave antennas, you will see the AM radios, the TV towers, are the tall, typically tall contraptions standing upright, and then they will transmit long wavelength signals. FM radios can be short antennas. So this picture of the electromagnetic spectrum can relate for you this basic property of electromagnetic waves. The fact that electromagnetic waves are characterized by the wavelengths. This is the characteristic size over which the electromagnetic oscillations happen, and also frequency. So there is a relationship between them. Here the wavelengths is shown on this scale, and the frequency is shown on the bottom scale. In this case, you can see the increase in frequency corresponds to decrease in wavelengths. The higher the frequency, the shorter the wavelengths. They are reciprocal of each other. And so we characterize part of this electromagnetic spectrum as visible light. That corresponds to electromagnetic radiation that has wavelengths of sort of size of about a micron or less. The wavelengths ranges from about 300 microns to 600-700 microns or so. This is visible light. Units here are meters, so half times 10 to the minus 6 is half a micron. Half of 1,000th of a millimeter is the typical wavelengths of the visible radiation, what our eyes have been evolutionarily developed to detect. And everything around this, higher frequencies and shorter wavelengths, or lower frequencies and longer wavelengths, is invisible light. Same exact process of electromagnetic oscillations, but something that antennas can detect rather than optical instruments. So this is what we're going to talk about this week, and well, rather today and next Thursday after your exam, is exactly electromagnetic waves that correspond to light outside of the visible spectrum. Short frequencies and long frequencies. Short wavelengths rather, and long wavelengths, high frequencies and short frequencies. And depending on your application, you may choose to use either electromagnetic radiation with high frequencies, or you may choose electromagnetic radiation with short frequencies. Often you choose which frequency range to use for a particular application depending on either informational content that you're trying to send, and discuss this later today. And if you're using electromagnetic radiation to observe something, you pick the wavelengths of the electromagnetic radiation such that the wavelength is shorter than typically the size of the object you're trying to observe. And this comes from the concept of diffraction that we discussed a couple of weeks ago, and I'll come back to today as well. Okay, so this was a little example of an antenna that can send or receive energy, electromagnetic energy over distance. That energy propagates over, through space. Doesn't have necessarily any particular medium associated with it. But you can also send electromagnetic signals by a wire or by a cable. Almost generally, you can send an electromagnetic signal through a device known as a waveguide. And this waveguide is are devices that look like this. It's basically a hollow piece of tube where the electromagnetic currents typically flow along it's a metal tube, right? It's typically copper, something that conducts electricity well. All of these waveguides look like this. They are hollow, typically, have nothing in the middle, and they're metallic. The way waveguides work is actually very different from electromagnetic radiation in space. If you're technical, there are TE modes, TM modes, antennas, or waveguides. That's not important. The important part to know about the waveguides is that they can transmit electromagnetic radiation only of specific wavelengths. There's an effect known as a cutoff frequency. It has to do with how electric fields, it has to do with the pattern of electric fields, the fact that the electric field always has to be perpendicular to the walls of the waveguide. This determines the frequencies or wavelengths that can propagate down the waveguide. If the waveguide is this big, so in other words, it has an opening of, I don't know, an inch on the side, longest size of this waveguide is an inch across, shorter side is say, a quarter inch. This waveguide can sustain electromagnetic wave with a wavelength of at least 2 inches. So the longest, or rather there's a shortest, well, let me rephrase. There's the longest wavelengths that can propagate through a waveguide, and any electromagnetic wave shorter than some specific size propagate down the waveguide, and electromagnetic radiation longer than that doesn't fit and doesn't propagate through the waveguide. And this concept you actually experience every time you drive through a tunnel. Again, turn your radio station onto some AM dial. I listen to news when I drive through the Caldecott Tunnel, 7:40 a.m., KCBS. Drive through the tunnel, you lose the signal. The reason for this is that the tunnels basically look like this. They're hollow tubes for cars and such that cannot propagate electromagnetic radiation whose wavelength is much longer than the size of the tunnel. The waves just don't fit. And electromagnetic energy stops at the entrance of the tunnel. It doesn't propagate very far. You can pick it up on the other end of the tunnel through electromagnetic energy that diffracts over the mountains. But through the tunnel, electromagnetic radiation doesn't propagate very well. And that, again, is the effect of the kind of the waveguide effect of the tunnel. So waveguides propagate waves that have wavelengths shorter than a typical size, transverse size of the guide. The other interesting effect about electromagnetic radiation, and again, both the waveguide effect and this Faraday cage effect have to do with the fact that electromagnetic energy doesn't propagate very well through metals. It gets attenuated by metals. Metals waste energy. Electrical currents flowing through metals heat metals up. Right? Remember demonstrations that we did when we discussed electrical currents. If you send high currents through a piece of wire, the wire may melt. It heats up. You boil water in the electrical teapot, by sending a high current through some coil. So electrical currents flowing through metals dissipate energy, and so electromagnetic waves that continuously send energy oscillating through oscillating electromagnetic fields don't propagate very well through the metal. They can propagate on the surface of the metal, but not through the bulk of the metal. And so metallic surfaces can be used as effective shields of outside electromagnetic radiation. This is known as Faraday cage. So, if you have an outside electric source, electrical currents would tend to flow towards the metal and then along the metal surface, but not penetrate through the metal. So you can use Faraday cages to shield yourself from electrical interferences. Here's an example. It's a Faraday cage. It's basically a box assembled out of thin wire mesh. The cage doesn't have to be very thick. The attenuation lengths for high frequencies in in metals are microns, very short. So let me again create an electrical disturbance. Have here the AM radio that picks up noise from this transmitter antenna. And I can stop this noise. I can stop the interference by placing the detector of the radio waves inside the metal box. So this metal box, known as the Faraday cage, is an effective shield. Doesn't have to be very thick. It all has to do with the fact that electromagnetic waves tend to like to flow along the surface of the metal rather than penetrate inwards. This actually is a very effective device. You know, during the exam, maybe I'll keep this box and I'll collect cell phones and put them in the box. That prevents reception. And again, you notice this very often if you walk into a building that's maybe an old building that has a lot of concrete, or not necessarily masonry, but has a lot of concrete. The way concrete buildings are built, concrete buildings have metal rebars, have structural metallic elements that support concrete when it's being poured. And so buildings like this typically has a lot of metal in the walls, and that metal acts as an effective Faraday cage, an effective shield of outside electromagnetic radiation. So when you walk into the building, you often notice if the building has a lot of metal in it, in the walls, the reception of your cell phone drops. And this is again from this Faraday cage shielding effect. If you walk into a newer building with lots of glass windows, they're okay. If you walk into a wooden building, wooden hut somewhere in the north, the wood doesn't shield you from electromagnetic radiation very efficiently. So again, this is known as the Faraday cage effect. Okay, last time I think we didn't actually have time to discuss this. Another example of a waveguide like this, but for visible light, is a fiber optic cable. Fiber optic cables work on a principle that's similar to waveguides in that they direct electromagnetic radiation through the body of this fiber optic cable waveguide. This works in the fiber optic cables through the effect known as total internal reflection, the fact that the light tends to stay inside the medium with high index of refraction, like glass, and doesn't tend to propagate outwards or refract outwards into the medium with low index of refraction, like air. So waveguides are tubes like this, built out of a material with high index of refraction. So this is plexiglass or glass, index of refraction of about 1.5, which means that the speed of light in this waveguide is about 50% slower than the speed of light in the vacuum. But the flip side of the effect is that electromagnetic waves penetrating through this medium that slows light down tends to stay inside this medium. And so waveguides can be used to send information. Waveguides can be used to send light. And in fact, since the light tends to stay inside the medium with high index of refraction or slow speed, waveguides can be used to shape the direction of the propagating wave, right? You can bend them, you can elbow them, and the light tends to stay inside this particular contraption. So these days, if you're receiving a cable signal in your house, or if you actually live in a dorm and somebody else is providing you a cable signal, most of the information sent by this cable, by a cable company, is sent over a fiber optic link. This fiber optic link can transmit information as a sequence of zeros and ones, oscillating electrical field intensity, ones meaning ones and zero, meaning an encoding of some informational item, numbers and data. And this data can be transmitted by a light signal where the information is encoded by the intensity of light, sort of like the Morse code. You know, you can, encode presence of light as a number 1, absence of light as a number 0, and then the signals of zeros and ones can encode numbers and characters, or you can encode some other type of, use some other type of encoding like the Morse code, like short versus long transmissions, dots and dashes. So, if you, Morse code aficionado, you can read signals like this. And so you can send information by chopping up the wave sent through the optical fiber, and then you can snake the optical fiber around the houses, send it underground, and then transmit the information very quickly and very efficiently. Now, the main reason now cable companies use optical fibers is because optical fibers can send a large amount of information in unit time. In other words, per second, optical fibers are more effective in transmitting information than a normal copper cable or a single wire. And the question is why? This was actually covered in the previous chapter, but we'll come back to this now because this has the bearing also on informational transmission by electromagnetic waves. So if you read, or if you still remember chapter 8, there was a discussion there about why fiber optic is better in terms of transmitting information than the wire. And is this because light has a very high frequency? Is this because electricity travels better in glass than in copper? Light travels faster than electricity, or light travels faster than sound? I would like to poll you now with your clickers. And let me start the poll. Right? 10 more seconds or so. All right, so let's look at your answers. Whenever they come out. Shows up? No? There you go. So two answers receive the most votes. A is that light has a very high frequency, and C, light travels faster than electricity. This isn't a trick. Where's my mouse? Oh, let me kill this. The actual answer is A. The actual answer lies in this so-called Shannon's information law, and that's actually not very difficult to understand. So Shannon's information law basically says that you can, if you transmit at high frequency, you can send more information per second. And that's sort of the basic premise, or rather Shannon-Hartley theorem. Mathematical form is here. You don't have to worry about mathematical form. The concept is that if you transmit at higher frequency, known otherwise as the bandwidth. Bandwidth technically is not a single frequency, but a range of frequencies, which are used to transmit information. But typically, this range of frequencies is proportional, is related to the actual frequency with which information is carried. So, for example, radio wave spectrum is typically divided, say for FM, into a specific set of stations. You know, if you turn an FM dial, there are stations sometimes every 0.2 megahertz, 98.5, 98.7, 98.9, etc. So these differences, these changes or steps in frequency is the amount of bandwidth, is the frequency range that is available for you to transmit information. If you go to AM dial, the AM dial stations are separated by smaller frequencies. 740, 750, seems like things are separated by tens, but the units are kilohertz, the units are 1,000 times smaller than when you change the FM dial. So AM stations are separated typically by 10 to 20 kilohertz, 10 to 20,000 hertz. FM stations are separated by 0.1 to 0.2 megahertz or 200,000 hertz. So the informational content in the FM radio is much larger. And so because this bandwidth and the frequency with which they send information is larger. And the reason to understand this is fairly straightforward. The way information is sent is by basically combination of zeros and ones. You know, this is 1, presence of light is 1 in a fiber optic, absence of light is 0. Or again, you can do dots and dashes as the Morse code. So if you have if you're sending information, you're sending it typically with some specific frequency or some specific wavelengths if you're talking about electromagnetic wave. So information is a sequence of high and low values of intensity. This can be 1, and this can be 0. This can be 1, this can be 0. Technically, actually, what happens is that you have something called a clock. You send information of specific frequency. It's an oscillating electromagnetic wave. It's maybe sinusoidal, and then you encode on it a pattern of zeros and ones. So you say, when the signal here is high, this is 1. And when intensity is low, it's 0. And so the higher the frequencies, the more often you can flip intensity from high to low. And therefore, the more bits you can stuff into the electromagnetic waves, the more information, the more switches from zeros and ones, and therefore more characters, more numbers, you can transmit per second. And this is really the basis of the essence of the Shannon's information theorem. And so again, the larger the frequency, the more frequency bands you can subdivide this band into, and the more information you can stuff into each particular band. And so this determines the informational richness or informational content of particular channel. If you're listening to AM radio, the AM radio sounds kind of dull. It's mainly you listen to, I don't know, talk shows and left or right wing, okay, I'll be politically correct, opinionated people on the talk shows, right? You typically listen to the voice. Voice has a relatively low range of frequencies, a relatively low amount of information. I speak with a frequency of, I don't know, 600, 700 hertz or so. So my informational bandwidth when I speak isn't very high. I tend to rumble a lot. Music has much more richness to it, much more informational content. Music can correspond, our audio range corresponds to frequencies as high as 20 kilohertz. And if you buy an MP3 or whatever it's called now, MP4, if it's on Apple audio, It's encoded also with high frequency sounds, and you can look at the informational content of the file. It usually says encoding done at the frequency of 192 kilohertz, or slightly worse, 90 kilohertz or 40 kilohertz. So there's typically, for high fidelity music, much more informational content. So FM radios can sustain that. FM radios can carry enough information to hear both, to hear stereo effect. Both left and right speakers can play slightly different intensities, whereas AM radio transmits mono signals. Both left and right speakers have the same information, and typically only enough to carry low frequency sounds. And the same with light. Fiber optics can transmit by light, by the frequencies measured in terahertz, compared to the copper cables that only transmits frequencies measured in gigahertz. There's a factor of 1,000 in frequency, and therefore almost a factor of 1,000 in informational content. Okay, so this has to do with information. The other way you can use electromagnetic radiation, like electromagnetic waves, is to observe stuff. So one specific example of a detector that's often used is a radar. And a radar uses two properties of electromagnetic waves. One property is the fact that electromagnetic waves travel with a fixed velocity, fixed speed, known as the speed of light, 300,000 kilometers a second. And so if you know how long the light has traveled, how long the radio wave has traveled, you can measure the distance. So that's how radars operate. Radars can be operated in the pulsed mode or in the continuous mode. There's a subtle difference in the detection technology, but the basic principle is still the same. The radar sends the signal out, waits for the signal to be reflected back, and that's the second property of electromagnetic radiation that's used by radars, is the fact that electromagnetic radiation tends to reflect off of metals very effectively. This is sort of similar to how these Faraday cages work. Faraday cages prevent electromagnetic energy of penetrating inwards, and so that electromagnetic energy has to either be absorbed by the metal or reflected backwards. And more often than not, electromagnetic energy gets reflected backwards from the piece of metal. And so if you send electromagnetic wave towards a metallic object like an airplane, that energy will be reflected backwards, and you can measure the time difference between the time when you emitted the signal and the time this antenna has detected the signal. The difference in time multiplied by the speed of light gives you twice the distance to the object. And so then you can send these signals, the antenna dishes typically are mounted on a carousel of some kind, so the antenna rotates around, sending a focused, very directional beam of radio waves towards specific spots, one at a time. And then it observes the signal reflected backwards and can tell then the operator of the radar where the object that reflected the light was, where it was at what angle, and the amount of time that it took for the light to propagate tells you the distance along the direction. You've experienced radars. I seem to be missing a slide. Actually, no, I'm not. The radars, as it turns out, can measure velocity as well. I'll get back to that in a second. But before we discuss this, radars can be used to detect objects, but the most fundamental property of the electromagnetic wave is the fact that electromagnetic waves are waves. They're not particles. In particular, they experience the concept of diffraction. They exhibit the property of being able to flow around small objects, or being able to spread out as these electromagnetic waves penetrate through small holes. This is known as diffraction. We discussed this previously. Diffraction is what ultimately limits the resolution with which you can detect objects with radio wave or even visible light technology. the fact that when electromagnetic wave, if it's sent as a beam in one specific direction, goes through a small hole, the direction of the wave spreads out like the energy from a pebble thrown into a pond spreads out in the circular waves on the surface of the pond. And the angular spread depends on the wavelengths. The angular spread is the ratio of wavelengths over size of the hole. So if the holes are small compared to the wavelengths, this ratio can be large, can be of order 1 in radian units or 60 degrees in the actual units. If the wavelength is exactly the same as the size of the hole, the spread is large. Can be 60 to 90 degrees. And so this produces a spot on the radar that's large and prevents an observer from detecting the size of the object reliably. The same happens when the electromagnetic wave flows around obstacles. Obstacles never cast perfect shadows, especially when the wavelength of radiation is large compared to the size of the object. Small objects don't cast shadows at all, which is one of the reasons AM radio can be detected over long distances, even behind buildings, because AM radio tend to have very long wavelengths on the order of hundreds of meters, and those radio waves tend to flow around, diffract around obstacles that are smaller than hundreds of meters. So to demonstrate this, this is a picture of the moon imaged with a light with the optical frequencies versus radio frequencies. Clearly, the resolution is better for short wavelengths electromagnetic radiation. The angular spread produced by these objects is smaller, the smaller than the wavelengths of radiation is. And so ultimately, the resolution of any device that senses electromagnetic waves is limited by the size of the device, size of the antenna, or size of the optical receiver, and the wavelengths of radiation. The smaller the wavelengths, the better in real size units the resolution is. This is what ultimately limits the physical resolution of any radio wave receiver. Radio waves have wavelengths of meters to sometimes hundreds of meters, which means the objects that you can observe will have to be larger than the wavelengths of radiation. Again, meters to hundreds of meters. Radars typically use high frequencies, frequencies of typically 100 gigahertz or so, with the wavelengths of millimeters, such that they can detect objects of the size of the millimeters. When it goes through the airport and it goes through the scanner, if you read carefully on the side, we discussed the fact that X-rays produce ionizing radiation and can cause biological damage to tissue. All security scanners in the airports have recently been replaced from X-rays to millimeter waves. And there are two reasons for that. One is the millimeter wave radiation does not cause biological damage as far as we know, unless the intensity is as high as in the microwave oven. So these scanners that everybody now is working through are biologically safe. But the second issue is that they use wavelengths with the wavelengths of about a millimeter, and that's good enough to observe any objects that might be in your pocket that are of the size of millimeters. Typically, security wants to know if you have a gun in your pocket, and the guns are large compared to the wavelengths of radiation produced by this security device. So essentially, every time you go through the airport, you're going through a radar. Effectively, you're going through a big device that produces millimeter wave radiation, detects it as this radiation is reflected off of you, off of metallic objects in your pockets, and then produces an image with the resolution of about a millimeter, given by that wavelengths of radiation. So that's one way to improve resolution, is to reduce the wavelengths of electromagnetic radiation. Reduce the wavelengths, get sharper image. And the other way, of course, is to, so this is one way to reduce the angular spread. Lasers dead. Is to reduce the wavelengths, and the other way is to increase the size of the hole, the size of the antenna that's receiving the information. Right, there are two numbers in this formula. You can either decrease the numerator or increase the denominator if you want to reduce the angular spread, which ultimately determines the resolution. So if the frequency of radiation is somehow fixed, if you cannot reduce the wavelengths, then the only way to improve resolution is to increase the large diameter, the increased diameter of the receiver. This is what's done often for radio astronomy. In radio astronomy, by definition, radio astronomy uses telescopes that operate at radio frequencies. The frequencies are typically limited by what kind of radiation can penetrate through the atmosphere, which is radio waves, or optical. But radio waves are convenient if you are trying to observe objects that produce a lot of radio waves, like pulsars, stars that actually produce a lot of intensity in the radio wave part of the electromagnetic spectrum. You want to be detecting them by some kind of a dish-like radio wave receivers. And so if your wavelength is fixed by the wavelengths of the source, like the stars, if you want to point to the star and resolve that star with higher and higher resolution, you need to bigger and bigger arrays have larger and larger diameter of the dish. Of course, producing dishes that are millimeter on the side is difficult technologically. So now radio astronomers often involve these large antenna arrays, which is a collection of dishes arranged in some pattern. Like here is the large, very large array, VLA, in New Mexico in the desert. It uses a lot of little antennas, well, little as in, 10 meters on the side, but they're all tuned in such a way that they all act as if they're all a single antenna. They all act coherently, and so the effective size of the antenna is about 100 meters in diameter. There's a new proposed experiment called square kilometer array that uses similar concept, uses a lot of little dishes, maybe 2 meters on the side or so, but arranged in an area of about a square kilometer that increases the effective diameter and reduces the, improves the resolution, reduces the pointing accuracy to fractions of a degree so that one can point to an object in the sky very precisely. A very similar effect is used by radars. You can do a similar trick where instead of if you actually want to place a radar on an aircraft so you can observe objects on the ground, it's inconvenient to build a very large antenna. The size of the antenna typically is limited then by the size of the hull of the aircraft, so to few yards across. And so the way to improve resolution in this case is to send radio waves in such a way that the radio waves sent from one point and the other point on the trajectory of the aircraft are very well synchronized, so that the very large area can be covered simultaneously, coherently, as if they were detected by a single antenna of the same size. This is done by producing a so-called synthetic aperture, producing microwaves that are very well synchronized, that are emitted coherently at different points in time and detected coherently. And so this synthetic aperture radar, or SAR, is a device that has an effective size of hundreds of meters and therefore can produce images with very high resolution. Here's the picture of the Pentagon taken by this synthetic aperture radar device. Obviously, it's taken by US military, not the Russian military, with high resolution. The other application of radar, as it turns out, radar uses a second concept in electromagnetic waves known as the Doppler effect. The Doppler effect, you guys experience Doppler effect often if you listen to an incoming car, or if you live by the track somewhere, if you listen to incoming train. The Doppler effect is the effect of the shift, a change in the apparent frequency or wavelengths of detected radiation from sources that move relative to the observer. So here, the easiest way to demonstrate it is with audio sound waves, but the same effect works with the microwaves and light and other electromagnetic radiation. The waves produced by a source that travels towards the observer the wave crests tend to be stuck closer together, and the apparent wavelengths of the radiation detected tends to be shorter, the frequency tends to be higher. If the source is receding from the receiver, the observed wavelength tends to be longer and the frequency smaller. So the objects that are traveling away from the receiver are shifted, their wavelengths is shifted towards longer wavelengths, towards redder colors, and the objects that are traveling towards the receiver tend to be shifted towards shorter wavelengths, bluer colors. The amount of the shift depends on the velocity. It's proportional to the speed for small speeds. And so if you measure the amount of the color change, if you measure the amount of the shift, you can measure the velocity, and which way the wavelengths of frequency shifts determines whether the object is, which direction the object is moving, towards you or away from you. Now, listening to this is most dramatic. Here's the whiny source producing a sound intensity, sounds at the frequency of a kilohertz, and you can hear the modulation of the sound. If I spin the object over my head, you hear higher pitch when the object moves towards you, and you hear lower pitch when the object moves away. If I move the object slowly, you don't hear much of the variation in the pitch. If I spin it fast, you hear a larger variation in pitch, larger range of frequencies. So the faster the objects are moving, the larger the change in frequencies, and you can use that fact to measure the speed. So this is used in Doppler radars, which are specifically devices that not only detect the direction towards an object, but can also measure their speed. It's used by police on the sides of the road to measure your speed and check it against local regulations and issue tickets. That happens to me too frequently, unfortunately. You can use this to detect speed of the wind by observing radio waves that are reflected off of the moisture droplets of water in the atmosphere. And you can use it, astronomers use this fact to measure velocity of the distant stars as they are moving away from us, as the effect known as the redshift. So this is a very well understood effect that can provide additional information to the radars. So the radars in practice can measure both the direction towards the object, but also by measuring the change in the frequency of the radio wave as it comes back from the object, the radars can also measure the object's velocity. Okay, so we've discussed the fact that you can produce radiation, electromagnetic waves, by sending electrical currents along the wire. But of course, the most common way to produce electromagnetic radiation is for any object just to be there, as it turns out. As it turns out, we are all filled with electrons. Luckily for us, these electrons have survived the Big Bang and the cosmic annihilation that followed. So we are built out of molecules and atoms that are all part of the periodic system, that are all built out of nuclei and electrons. And we discussed when we talked about heat is that we measure energy, we measure heat energy we define temperature as the kinetic energy in the shaking random motion of molecules in our bodies. We all have a typical body temperature of 36 degrees centigrade or roughly 310 degrees Kelvin, which means that electrons in our body shake, move with the characteristic energy that's larger than something that may be cooled to lower temperatures by liquid nitrogen, or the typical intensity of the typical kinetic energy of molecules in our body is larger than the kinetic energy of molecules in the environment if the environment is at lower temperature. So the fact that we are full of charged particles, we are full of electrons and the nuclei, and those electrons nuclei shake continuously, means that all of our bodies are continuously producing electromagnetic radiation. And that electromagnetic radiation depends on the specific frequency, the intensity, and the frequency we emit depends on the temperature. The higher the temperature, the more our electrons are shaken in our body, the higher the frequency with which electromagnetic radiation is emitted. This is known as the black body radiation law. Is the fact that the intensity of radiation, the total power emitted by any warm body that sits at a non-zero absolute temperature, goes up as the forced power of temperature. So the fact that our temperature is 310 Kelvin, and today, the room may have a temperature of 290 Kelvin, the difference of only about 3% or so. The fact that the radiation emitted is proportional to T to the forced power means that we emit about 12% more energy per unit area than we absorb. Or we emit 12% more energy into the environment that gets emitted by the environment towards us. So you can use that fact to observe warm bodies. You can measure the intensity of the electromagnetic radiation produced by them, and the higher that intensity is, the warmer the object is. This is again the essence of the black body radiation law. And the second fact about black body radiation is that the frequency with which the intensity is emitted also depends on temperature. The higher the temperature, the higher the frequency, or the lower the wavelengths. So warm bodies, such as our sun, whose surface temperature sits at about 6,000 degrees Kelvin, produces radiation at lower wavelengths, higher frequencies, than objects that are at lower temperatures. The wavelengths is inversely proportional to the temperature. So the fact that our body temperature is about 300 Kelvin and the sun's temperature is 20 times larger means that the sun produces radiation which with wavelengths on average 20 times shorter than the wavelengths we produce. So for the sun, that wavelength corresponds to wavelengths of about half a micron or so in the visible range, and we all produce radiation at 20 times longer wavelengths known as infrared, sitting at the wavelengths of about 10 microns or so. Nevertheless, we produce a lot of radiation. I think the book has this quote there saying that you're all as bright as light bulbs. You're actually brighter than that, at least kind of conceptually speaking. You all got to Cal, so you're all very bright. But physically speaking, you're actually much brighter than a light bulb. If I place you in vacuum, it's a cruel thing to do. But if you were in space, your body would radiate about 1 kilowatt of energy. So you're actually as bright as one of those bulbs, or you emit as much radiation, as much energy as a rice cooker or a microwave. It's about 1 kilowatt worth of thermal energy. Of course, when we live in a normal environment, we also absorb almost as much energy back. The environment around us sits at about the same temperature, slightly lower, so we always continuously absorb radiation from the environment. Also, our clothes can stop some of the radiation from escaping. And so, on average, the difference between our intensity emitted and intensity absorbed is about 100 watts or so, which is as much as the light bulb emits. And the only difference being is we emit in the infrared range, whereas the light bulbs emit in the visible. So let me show you this fact, the fact that you are all bright. If we can switch to the camera. I have here a infrared camera. And these are all your images, your thermal images. Yeah, you can wave over there. This is the top of the Pimentel lights. These are all you guys in the back row. Wave, you're on camera. And these are all you guys in the middle. You see that you're all very bright. You are looking like white ghosts. You emit a lot of radiation, much more than the chairs you're sitting on. Your chairs are sitting at a lower temperature and emit less intensity per unit area. Blue here means colder, as it should be. Red is warmer, and white is red hot. You're hot. Microwaves are interesting things. Microwaves are is an example of electromagnetic, well, these are not microwaves, infrared radiation. It's infrared radiation, corresponds, if you can switch back to the screen for a second. Microwave infrared radiation corresponds to wavelengths here of, where's my pointer, of about 10 microns to a micron or so. Near infrared corresponds to the wavelengths that are just longer than the visible light, perhaps micron or so. Farther infrared corresponds to typical temperatures of the human body and wavelengths of about 10 microns or so. So we can use infrared radiation to detect warm bodies. This is known as infrared imaging. Human bodies produce 10 micron wavelengths, so if you tune the camera, this camera is tuned to the wavelengths of 10 microns or so. If you're trying to image bodies that are hotter than that, you would typically tune them to shorter wavelengths. Infrared remote controls work actually exactly on the same principle. They're not lasers, but they're devices that produce light, except in order to not distract you from your TV screen, they use light at infrared wavelengths somewhere away from the visible range. Of course, night vision goggles use the infrared technology, sort of similar to this camera. And there are actually two types of infrared goggles. They're passive devices that just use thermal image from a warm body, or that can detect people. So that's used by combat troops, for example, to detect enemies that may be crawling along the surface somewhere, trying to spring a surprise attack. You can also use active devices, which would have a transmitter and a receiver. This is, I guess we'll probably do this demonstration here. So this is an example of an infrared light. It's a dark light. Well, dark light can use UV or can use infrared. This device produces light at the near infrared frequency. It looks black, but if I were to connect it to a thermal camera that's sensitive to a micron wavelengths, you could see reflection from it, and you can use it as a floodlight or as a flashlight. So U.S. military also use these active devices, in particular sharpshooters that can shoot at night, would typically have a source of near infrared radiation, typically at the wavelengths of the micron, and the night vision goggles that can detect near infrared frequencies, near-infrared wavelengths of about a micron or so. So that works very well. Of course, it only works very well if you're fighting against the enemy that doesn't have a similar night vision goggles. Otherwise, your sharpshooter will have a big, sort of shoot here light bulb on their head. So it's used actively by US military when they're fighting against the military that's not similarly equipped, somewhere in Afghanistan or Iraq, for example. If you're fighting against the enemies that may have night vision goggles, you probably want to use a passive device that will just look at thermal temperatures. Heat-seeking missiles like Stinger, the famous American heat-seeking missile, or Strela, the Russian copy of it, use infrared technology, and I'll probably show you a movie of that next time. So here are some of the infrared imaging pictures that can be detected by night vision goggles, where the color corresponds to a change in temperature. The night vision goggle technology, or this infrared sensing technology, is extremely helpful if you want to analyze heat leaks in your house. Again, measuring the intensity and the frequency of light will tell you hotspots, so it will tell you where energy is escaping and where you need to add insulation. You can measure stresses and temperature variations across a human body, or detect perhaps an enemy combatant. Infrared imaging also can be used to monitor effects of global warming, or just in general patterns in the climate and the climate change, as Professor Moller was discussing on Tuesday. This is a picture from a satellite looking at the infrared image of our planet, and where you can see clearly cold spots near the poles and hot spots on the surface. And as it turns out, similar infrared, but very, very, very far infrared image can be taken of our universe. This is a picture from a WMAP satellite, otherwise known as the Wilkinson Microwave Anisotropy Probe, that looks at the very, 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 very far infrared, or rather microwave frequencies of about 40 gigahertz or so. These microwave frequencies can be used to look at pattern of hot and cold spots on the sky. This pattern of cold and hot spots corresponds to places in the universe that used to be very hot and very cold about 100,000 years after the Big Bang. They emitted at that point high short wavelengths, high energy radiation that has been redshifted, that has shifted towards lower frequencies by expansion in the universe. Nevertheless, the thermal image of the universe, this picture, with the middle plane corresponding to our galaxy, that's on average much hotter than the surrounding environment, determines the fluctuations in the temperature and determines the non-uniformities in the temperature and the density of the very early, of the matter in the very early universe. This corresponds to a temperature map that on average looks at the temperature of about 3 Kelvin. That's the temperature of our universe. That's the temperature of anything in empty space. The entire empty space is filled with these microwaves. There's no such thing, in fact, as the absolute zero in the universe. The entire universe is filled with the gas of photons produced by the Big Bang that corresponds now to this roughly 40 to 100 gigahertz frequency range, or the temperatures of 3 Kelvin, and temperature fluctuations of as much as 200 Kelvin on top of this correspond to patterns of hot and cold spots in the early universe. So we'll discuss this in much more detail towards the end of the semester, and what we can learn by observing these patterns. What we'll do on Thursday of next week is we'll discuss further applications of infrared and UV technology, in particular heat-seeking missiles and such. In the meantime, I wish you good luck on Tuesday. I'll see you there bright and early at 9:30 with a piece of paper for a cheat sheet and lots of knowledge in your head. See you then.